All right, so welcome. Yes, this is the last class. As you know, we had a technical glitch on Friday, and it's only gotten better or worse. I'm not exactly sure how to explain it. Basically, for my first class an hour ago, my virus scanner decided that it was going to block learn.unbc.ca. And so the only way that I am actually communicating with you right now is because I actually had to uninstall my virus scanner to allow me to actually access the UNBC website, which is somewhat concerning and somewhat weird, and it's just crazy. So that's what's happening there. I have not figured out the problem with the tablet. It is an enigma. I have tried a bunch of stuff over the weekend and it is not working. I will explain what I'm going to do in just a few minutes. But what I will tell you is that I have put the keys online. So the answer key to problem set 8 is now available, and the answer key to the sample final exams is now available to you. So you can kind of get an idea of what the questions are on the exams you were always had access to, but now you have access to the keys to see the work solutions. With regards to your presentation grades, I am waiting for marks from one TA. Unfortunately, I had asked the TAs to get me the grades by Saturday noon, and they have yet to, one TA has yet to do so. In addition, I sent emails to a number of people because the TAs had not gotten grades from select students, so I have been sending emails saying, you need to get it to me or else you're going to get a 0. It's the way it works, sadly, in that regard. So as soon as I get the grades from the last TA, I will post everything online and deal with the individual students myself. That's where it's going to go. With regards to today's class, I want to go through the material. That is, I want to go through the, I want to go through the lecture portion of it, and then I will make available the work solutions. So I will post the work solutions to all of the examples that I'm going to talk about today in class up on Blackboard. And so they're all going to be there. And the other thing that I'm going to do, if I can get my tablet working properly, I will go through and actually complete those solutions for you as well. Sorry. My phone's not on vibrate. I don't know why. All right, so that is the plan. Does anyone have any questions or comments? Okay. Where was I going to go? All right, so let us go through and look at the course material. So we didn't get to this last day, but this is where I would have ended off in the video that you saw. And in this, we were able, because we're not operating at 298 Kelvin, you were needed to use thermodynamic data, delta H and delta S, to calculate the free energy at 338 Kelvin, and then from that calculate the standard cell potential at 338 Kelvin. That was part A. That was what was covered last day. Part B is an application of the Nernst equation. 65 degrees Celsius happens to be 338 Kelvin. So that's not a big deal. But you don't have 1 mole per liter or 1 bar partial pressure. You've got different concentrations of the solutions, and oxygen comes from the air, and oxygen in the air is about 0.209 bar. 21% of the air is oxygen. So what is the cell potential under these non-standard conditions? And the answer to that is the answer to part A was 1.17 volts. The answer to part B under the non-standard conditions is 1.162 volts. So it doesn't change much, but there is a slight change. For part C, is to determine what methanol flow rate must be used to produce 150 watts of usable power, given that the cell is 55% efficient. Well, 150 watts is a unit of energy, and to convert that back to something that we can work with, power equals volts times current, P equals VI. And so we are able to, excuse me, I humbly apologize. Someone has been trying to get a hold of me, and I'm just going to take a quick break here to actually deal with this. Please excuse me. This is the third time they've called. My humble apologies. That was ridiculous. All right, so the cell is 150 watts. Current, from the current, you can get the moles of electrons that are being transferred. And then from that, you can figure out what methanol flow rate must be used. So take into account the 55% efficiency can be done at pretty much any time. If you calculate the current, realize that only 55% of that is effective, and so you need to have a larger number such that this larger number times 55% is what you would get using from 150 watts. Anyways, it probably makes a lot more sense in the work solutions. 150 watts of power is what a vehicle would need to run down the road under, basically to keep power at about between 60 and 80 kilometers an hour. So just out of curiosity, anyone have any idea how much methanol would be needed to do that? Where do you think? How much in terms of flow rate? 1 milliliter per minute, 1 to 10 milliliters per minute, 10 to 100 milliliters per minute, or greater than 100 milliliters per minute? And you know, if you've done this work before, if this was your project, you might have an idea, but how much methanol flow do we need? $10 to 100 milliliters per minute. Anyone else have anything they want to offer? This is literally just to keep a car moving down the road at constant velocity, somewhere between 60 and 80 kilometers an hour, about 150 watts. 10 to 100. The answer is 6 milliliters per minute. So that's not a lot, but it's basically the amount of fuel that one would actually burn too. So it's comparable to the amount of fuel that would actually be burned in order to keep this vehicle in operation. But you'll be able to calculate that at some point in time as soon as you see the work solutions. Voltaic cells, corrosion is the voltaic cells that we don't want to occur, but they occur spontaneously. And when this occurs in structural materials such as steel and iron, you get oxidation, you get rusting of the material. So in this example, you're given the standard cell potential, a 1.282 volts for that, and you're asked for the non-standard cell potential given that the oxygen partial pressure is 0.209 bar. Oxygen is the only thing that has any variability in here. You're working with solid iron going to solid iron oxide, and both of those two have unit activity. The only thing that can vary is oxygen. Now, given that oxygen is 0.209 bar, and oxygen is a reactant, would you expect the non-standard cell potential under these conditions to have a lower potential or a greater potential? Should it be less than 1.28 volts or greater than 1.28 volts, given that the oxygen partial pressure is 0.209? Think of it as a driving force. Is it going to have a greater driving force, or is it going to have a lesser driving force, given that this is 0.209 bar rather than 1 bar? Greater or less? greater, greater. A couple people are saying that it's going to be greater. Now, if we go back and we look at this oxygen partial pressure, if this is 1 bar, you have 1.28 volts. If this is the driving force, and this is a spontaneous process, if I increase the oxygen partial pressure, it would have a greater driving force or greater interest in going to products. So if oxygen partial pressure is greater than 1 bar, this number should be greater than 1.28 volts. Since we have an oxygen partial pressure of 0.2, which is less than 1, you can imagine if this actually goes all the way down to 0. If this oxygen partial pressure goes to 0, then you would not have this reaction occurring at all, and the cell potential would be 0 volts. So since this number is less than 1, this number should probably be less than 1.28. And it is 1.275. Not a large change, but it is less. And we can explain it given that the partial pressure is less than 1 bar. If we want to protect metal from unwanted oxidation, we can do this through a process called galvanization. Galvanization coats the metal that we care about with a metal that we don't care about. So you have structural steel that you want to protect. You protect it by coating it with something that oxidizes more readily, and these things are called sacrificial anodes. Now, your automobile body, the metal components of your automobile body are dipped in zinc, which is a common and inexpensive sacrificial anode. They literally have a huge vat of molten zinc. Automobile body is dipped in, got out. Similarly for nails, you can go to the hardware store and you can buy bright nails, and those bright nails are pure steel. They're not protected from oxidation. If you look for the dull, ruddy colored ones that are some, very odd gray colored, they're not shiny at all, they are hot dipped or cold dipped galvanized nails. They're dipped in zinc and they now have a layer of protection on them. As I mentioned, zinc is very common because it's inexpensive, but if you want to protect something that you can't readily change the sacrificial anode on, like a pipeline, you would use magnesium. Magnesium provides you with greater protection, but it is more expensive. And we don't have the ability to do it here because we got a tablet issue, but we want to confirm that zinc and magnesium will protect iron by calculating the cell potentials. And what one would expect is if the forward reaction were to proceed, that is, zinc is oxidized and iron is reduced, we're protecting the iron, then both of these potentials should be positive. And if I'm telling you that magnesium is better than zinc, magnesium should have a greater cell potential than that of zinc. Before I get on to concentration cells, just a quick story associated with this is that when I moved to Prince George, I discovered, to my surprise, pleasant surprise actually, that they don't put salt on the roads. Many cities are starting, or have for a long time, used salt to de-ice the roads. So Edmonton, Calgary, and Toronto, the greater Toronto area, is hugely invested in putting salt on the roads. To the point that when I was there a couple of years ago, the roads were white with salt in February, March, when it had melted, but there hadn't been a lot of rains to come clean it up. In those areas, the rust protection on your vehicle is often reduced. If you go and buy a vehicle, in many jurisdictions, they offer you a 5 or a 7 year rust-free guarantee because the galvanization on the body of the iron of your vehicle is sufficiently thick that under normal conditions it will last 5-7 years before all of the zinc is used up and it starts rusting away the metal. In cities like Toronto, Edmonton, Calgary, I think Vancouver still does it, I'm not sure, they have either reduced that rust-free guarantee or eliminated it completely because of the amount of salt that is thrown on the roads. And salt facilitates this reaction. Basically, if there's water and salt present, or salt water present, I guess would be the correct thing, you end up with the zinc just oxidizing for no purpose whatsoever. It's not really, it's just getting used up. Does anyone have any questions on this material before I move on to concentration cells? All right. A concentration cell, as was defined previously, has both half cells containing the same entities, same electrodes, same reagents, but at different concentrations. So in the cell diagram, or in the picture that is below, you have two zinc electrodes, you have zinc ions in solution. One of them is your reference cell, and that one is presented as 1 mole per liter zinc. It doesn't need to be 1 mole per liter, but that's standard. And the other one has X moles per liter. Because there is a concentration difference, there is a voltage difference. So when we talked about osmotic pressure earlier, you talked about the reason that osmosis occurs is to try to make the concentrations equal. Well, you can see it as osmotic pressure, or you can see it here as an electrochemical potential. You want to make the concentrations equal. And by measuring the voltage difference, you're able to calculate the difference in concentration between the two half cells. So under standard conditions, where both of those two half cells are at 1 mole per liter, their concentrations are equal, so there is no driving force. So the standard cell potential in a concentration cell is 0, and we can now use the Nernst equation to calculate the concentration. Commonly, it is used to calculate the concentration of metal ions in equilibria systems, would be one example. If you were in lab this term, you would be doing something like this. You would have not a cell that looks like that, but the equivalent cell setup in wells, and you'd be able to measure the voltage difference between a standard cell and your unknown, and determine what the concentration is. In the example we have here, we have, reading the second line, 1 cell contains 0.5 moles per liter of copper nitrate, period. That is your standard reference cell. It's not 1 mole per liter, it's 0.5, but as long as we know what it is, we're good. The other cell is a mixture of copper nitrate and hydrochloric acid, and you can see from the bottom that forms a complex ion, CuCl3 2-. So the copper ion concentration is reduced because of this equilibrium, and when they measure a voltage as presented here, you can figure out how much copper ions are left free in solution. If you know how much are left free in solution, you're able to set up a complete ice table and determine the equilibrium constant. Solubility examples are done like this. Complex ion formation examples are done like this. You could have done one of these in lab had it been a normal year. And as I mentioned, I will be going through and doing this for you once I get my tablet back in operation. The first concentration cell was the standard hydrogen cell, and it was used to measure the pH. Okay, the hydron concentration in a solution. This is an example where we have a platinum electrode, because it's inert, hydrogen gas at 1 bar, and an unknown concentration of hydrogen ions in solution. So on the left-hand side, you have hydrogen gas being bubbled through, and you have the anode being the electrode being platinum. It just needs to be someplace for electrons to get put through. And hydrogen is in contact with the electrode and in contact with the solution, and so you have that on both sides, and that ends up, forming your concentration cell. And the only unknown in this entire process is the unknown hydrogen ion concentration. That is the unknown, and with everything else being known, we can go through and calculate that value. This pH electrode and other ion selective electrodes have come a long way. This would be a typical electrode, ion sensitive electrode on the right hand side, and it works by having a membrane at the bottom, and this membrane preferentially allows only one ion to pass through that membrane. Ideally, only one ion can pass through that membrane. If it is a certain type of glass, you end up with a pH electrode. And all of this funny workings here are what you would see over here. Electrodes coming in and solutions of known concentration, that's your reference half cell, and your sensing half cell contains, again, a known concentration of hydrogen ions, and you're measuring the voltage across that glass membrane. That's how ion selective electrodes work. They have for fluoride, if Prince George fluoridated the water, or places that do fluoridate the water, you would have literally just a probe that is stuck in the stream, and you would be constantly monitoring the fluoride ion concentration that is going out. If you're using chlorine to do to disinfect the water, you could do that. We had one presentation about the use of chemicals to measure the hypochlorous concentration in swimming pools. An electrode is possible that could do the exact same thing. So it would be nothing more than getting a sample of water and doing a dip with an ion selective electrode, and it would tell you what at least the individual chlorine concentration is, and you would be able to know what you need to do to maintain that pool. Are there any questions on concentration cells? The last example is that of electrolytic cells, and those that proceed with applied electricity. So you need now electric current, electric voltage to come in and turn what is normally a non-spontaneous process into a spontaneous process. The one example that we had at the very beginning of the thermodynamics unit actually was the hydrolysis of water. It takes something greater than 1.22 volts to hydrolyze water to give you hydrogen and oxygen gas. So applying a potential changes the reaction conditions to make the process spontaneous. Electrolysis is a very common industrial process. Electricity is fairly inexpensive, and it can be used to control reactions. One example is that you are refining a metal. If you, everything from gold to aluminum and all the metals in between there can be refined by electrolytic systems through taking an impure ore and depositing the metal onto a pure electrode. Cathode is the word I wanted there. If you're going to do electroplating, that is just one application. Instead of complete refining of the ore, you're refining it such that it coats a bumper or a hood ornament or a toy or some jewelry or whatever the case is. And so electroplating is just an example of electro-refining where the product itself is the marketable thing. Some of the more some of the more reactive chemicals are produced through electrosynthesis. It is a convenient way to produce them. We talk about the hydrolysis of water into into hydrogen and oxygen. Well, if you have a really high salt solution, so brine, high concentration of sodium chloride, when you electrolyze a brine solution, you get hydrogen and chlorine gas. And so now you've changed the solution that you're electrolyzing, and you can get different components out. So things like chlorine and fluorine, sodium hydroxide, are all produced through the electrolysis of different solutions. And then they're packaged up, and they're sold and used in laboratories or other industrial processes. And the last thing I want to do here is just look at this. If you have friends and family that work in Kitimat, Kitimat has a massive aluminum refinery, And so they are doing quite literally this electrolytic process to refine aluminum. And this is a cell that operates at very low voltage, 5 volts, but you're operating at 100,000 amps because the amount of material you need to go from raw ore to refined metal is huge. Current is the major part of this. So how long does it take to produce 1 ton of aluminum? And given those electricity costs and in a cell efficiency, how much does it cost to produce that aluminum? And that's what I would like you to speculate on. Is the cost to produce 1 ton of aluminum in terms of electricity less than $1, 1 to 10, 10 to 100, 100 to 1,000, or greater than $1,000? Please. What do you think? Anyone have an idea? Most people say $10 to $100 or maybe $100 to $1,000. The actual cost to produce 1 ton of aluminum under those conditions is actually just over $2,000. So aluminum is an expensive metal to produce. Yeah, $2,024, but with sig figs it's around $2,000 to produce that amount of aluminum. And the last example that we're going to have in this course is that of electroplating, where we are now depositing a metal onto a substrate to provide either a decorative or a protective finish. And in the example that's presented there, we are gold plating cutlery. Unfortunately, that's not my house. I'm stuck with the nickel plated dinnerware. If you do happen to have gold plated dinnerware in your home, I'll take an invitation for dinner. Chrome plating of automobile parts and toy parts is also a common electroplating process. The thing we need to control here, again, is the current. And the current allows us, measuring the current allows us to know how much we have deposited. And so the equation that relates current to charge is simply Q is equal to I times T. Q is the charge, current is I, and T is the time. And we can figure out how much charge is transferred. We can convert that to moles of electrons and then moles of the reactive element or metal that's being transferred. And so in this final example, we are electroplating a 5-piece dinner set. Has a surface area of about 190 square centimeters, and we want to determine both the mass of nickel required to plate it and the electrolysis time if you use 300 amps to electrolyze in the electrolysis process. The answer to these questions, if you'd like to attempt them, is that it takes about 8.5 grams of nickel to do the plating, and it takes a whopping 93 seconds to for that electrolysis to be complete. Then the finished utensils are taken and run through a bulk polisher and packaged up, and you were able to buy them. Away you go. So that is, ladies and gentlemen, the course. And to summarize everything we did, we looked at electrochemical cells, galvanic, electrolytic, and concentration cells. And then we looked at the relationship between these processes. What links free energy, electrochemical cell potential, and equilibria mathematically. And now we have the ability to do things like calculate equilibrium constants at various temperatures, convert cell potentials, and that type of idea. So that, ladies and gentlemen, is what I was going to be covering, well, today in a little bit. But I will post the final work solutions, and if I can get my tablet and laptop talking to each other, I will go through and create these work solutions in real time. Thank you very much for your time and attention. And is there anything I can answer for you? Any questions? Not a problem, Ben. Are we good? Can I talk about the units on Q equals IT? Sure. Q has units of coulombs. Q has units of coulombs. Current is coulombs per second. And T is, of course, time in seconds. And if you know the charge in coulombs, then you can use Faraday's constant to convert that to moles of electrons. So from the charge in coulombs, you can convert to moles of electrons. And then by knowing the stoichiometry of the reaction, how many electrons are transferred, you can convert to moles of metal. Does that answer your question, Efren? What's this cartwheel thing? Sorry, not sure what you're talking about. What do you mean you saw it on my channel? Are you snooping outside of the course channel? And you heard I did it for the other class. Well, they are loudmouths now, aren't they? Really? I did it for the other class? Shouldn't I be limited to 1 cartwheel per year? Not good enough? Can't you just go watch their video? If I say please, I don't respond to peer pressure, ladies and gentlemen. Sheesh. What do I look like? Pretty please might do it, actually. Really? I don't even. Did you all show me your face during your presentations? No. How many people did? 1. 1 person projected their face. And 2 other people showed me their pets. Oh. Okay, we're figuring this thing out. Oh wait, I can do this one. So the theory behind a cartwheel is that I don't kill myself. So I need some people on here to kind of promise that if this goes awry, you'll end up dialing 911 and at least telling them where I'm at, please. Is that going to work? Is that going to work for me? No. So just realize that two things come out of this. 1, I have only done this once in the past 3 years because I wasn't teaching chemistry the last few years. And 2, I put on a few pounds with COVID. So just hold on to that thought for now, okay? So cartwheel ends up me going that way. Oh, why me? Why me? Does that work for you? Oh my goodness. Oh, I really need to go to the gym more. Oh, that hurt. Now you're motivated to study. All right, everybody. Have a great summer. We'll chat with some of you before the final exam. As I said, everything's online, and we will... yeah, have a great summer. And if you have any questions, please, the TAs are available, but so am I. Take care.